Once in 27.5 million years, Earth undergoes massive cataclysmic events, as a Chinese proverb says. Fortune does not come twice, misfortune does not come alone. The catastrophic geological events such as massive volcanism, species mass extinction appear to occur in clusters. Boom! Volcanoes thundered, shaking the whole of the Earth. One after another, a chain of volcanoes erupted, taking place in repeated bursts. Over the next 40,000 years, a mere blip in geological timescale, this calamitous event, known as the End Triassic Age catastrophe, took place about 201 million years ago. This wiped off more than 80% of all species from the face of the Earth. Why did this cataclysmic event occur when it did? Was it random, or was it a part of a pattern, a grand cosmic rhythm that we are yet to decipher? From extinctions to depletion of oxygen level in oceans, sea level fluctuations, a massive volcanic activity called flood basalt eruptions, and changes in Earth's tectonic plates, Earth's history is punctuated with several such cataclysmic geological events. Using new dating techniques to accurately date 89 major geological events in the past 260 million years, a research team led by Michael Rampino, a geologist and professor in New York University's Department of Biology, argues that there is a 27.5 million year cycle to these events. While the actual causes that generate the periodicity are yet to be unraveled, researchers implicate the enigmatic and elusive dark matter in the onset of violent geological events that periodically change the face of Earth. If indeed this pattern is true, the last cluster of geological events took place about 7-10 million years ago, which means we can anticipate the next big one in about 15-20 million years. Triassic Eden. In the early period of Earth's existence, there was only one giant landmass on the Earth, Pangaea, with two interconnected regions, Gondwana and Laurasia. During most of the Triassic period 252-201 million years ago. The Indian subcontinent, Antarctica, Australia, Africa, and South and North American continents were but different regions of Gondwana. The Himalayan range, America and Africa were yet to appear in the Earth's history. This single landmass was surrounded by one single superocean, Panthalassa. The incipient Tethys Sea was making its appearance between Gondwana and Laurasia. Lush growth of conifers, ferns, and a now extinct group of plants known as the seed ferns Pteridospermatopsids dominated the land mass. Coniferous forest had trees that were 30 meters tall, and the drier regions were rich with fern prairies. The ferns and conifers came in a wider variety than what we find on Earth today. There were fern, shrub and woody vines. Most notably, there were hardly any flowering plants. Small, herbivorous synapsid, or mammal-like reptile, called Lystrosaurus, was the most common vertebrate snacking on these vegetations. Tanystropheus, another Triassic period reptile, 6 meter long, with a neck extraordinarily long, equal to the length of its body and tail combined, competed. Shallow water bodies were full of a distinct group of amphibians known as the temnospondyls that physically resembled modern crocodiles, at 4 meters in length. Along with trilobites, ichthyosaurs, aquatic reptiles, with the appearance of porpoises, commanded the world ocean. Lacking gills like the modern fish, the ichthyosaurs breathed air like modern whales. If we go on a time travel back, hardly a few species would be familiar to us. In short, it was a world not anything like today. The day the Earth stood still, mighty volcanoes flared up and exploded in a region known as Central Atlantic Magmatic Province Camp. This region evolved into the Proto-Atlantic Ocean. Energetic outbursts set various continents in motion and literally ripped the American continent out of the African region of the Gondwana. Even today, the west coastline of Africa would snuggle and fit like a zigzag puzzle along the eastern coast of the South and North American continents. The energetic jolt pushed the African, Australian, Indian and Antarctica landmass in different directions. The birth of continents was accompanied by massive death of animals, plants and marine creatures. The volcanic activity spewed huge amounts, around 2 million cubic kilometers, of lava and gas. Carbon dioxide, sulfur and methane ejected by the volcanoes polluted the Earth's atmosphere. Excess carbon dioxide dissolved in the ocean, making it acidic. Deadly hydrogen sulfide in the air, precipitated as acid rain. Oxygen levels in the ocean plummeted like a falling stone, making it hard for marine creatures to survive. High concentrations of hydrogen sulfide are toxic to plants, and the ferns and conifers died. So when the ocean became acidic and depleted of oxygen, the trilobites, a group of animals that lived in the oceans for close to 300 million years, were completely decimated. Ichthyosaurs barely managed to survive. All but one, Tuatara, presently endemic only in New Zealand belonging to sphenodonts, an ancient reptile family, could get through. About 80% of all the species that lived became extinct during this end Triassic event. As they say, one man's meat is another man's poison. Dinosaurs had appeared 240 million years ago during the Triassic period. Yet, they were small, bipedal creatures hardly making a mark during the Triassic epoch. With other competing mammals gone, post-cataclysmic and Triassic event, dinosaurs catapulted into the preponderant animal on the landmass. Deccan Traps to Reunion Island. Carefully look at a relief map of Earth. From the Deccan Traps in the north, we can trace an imaginary line going along the Laccadive Islands, Mauritius Islands, to Reunion Island down south. We can observe that the ocean floor is studded with strings of islands and atolls along this line. This chain of islands and atolls were created by what is known as the Reunion hotspot. Like the onion, the Earth comprises different layers: the inner core, outer core, mantle, asthenosphere, or the top mantle, and the crust. A region that includes the uppermost portion of the asthenosphere and the crust called lithosphere. Surf on the top of the asthenosphere is highly viscous, semi-liquid magma. The lithosphere, holding the continental and oceanic crust, is broken into discrete sections known as tectonic plates. Some of the major lithosphere tectonic plates are African, Antarctic, Eurasian, North American, Pacific, and South American. The Indian plate, consisting of the Indian subcontinent, the Bay of Bengal, Arabian Sea, and a part of the Indian Ocean basin, is a minor tectonic plate that broke away from the Gondwana 100 million years ago. Presently, the plate is moving in the northeast direction at 5 cm (2.0 in per year. The collision of this plate with the Eurasian plate resulted in the formation of the Himalayas around 55 million years ago. Even today, the Indian plate is moving, and the crust beneath the Himalayas is still folding. Once in a while, a mantle plume rises up, erupting into a massive, hotspot, volcano. Unlike the usual volcanoes, like the Ring of Fire in the Pacific, that occur along the boundary of the tectonic plates, hotspots are unique. They occur at abnormally hot spots on the mantle called mantle plumes. The molten lava goes up through a long, narrow tail that originates in the mantle. Once the plume head reaches the lithosphere, it melts the rocks at its base. The melted rock, known as magma, seeps through the cracks in the crust to form volcanoes. About 65 million years ago, a hotspot developed and exploded under the Indian plate. When such a hotspot volcano becomes active, they emit copious lava flow in waves, one after another. This resulted in the formation of the Deccan Traps. When the molten lava solidifies, they create step-like hills. Such geological structures are called trap, meaning stairs, in Swedish. The lava from the Deccan Trap volcanism that lasted for about 30,000 years resulted in a 2,000-meter thick layer of solidified flood basalt covering an area of about 15 lakh square kilometers. The hotspot again erupted 60 million years ago. But by then, like the train rolling over the rails, the Indian plate had moved northward substantially. Hence the location of the hotspot was no longer under the Indian subcontinent but was under the Indian Ocean. The magma oozing out solidified and became what are today the Laccadive Islands. When the hotspot again erupted 57 million years ago, the plate moved further, and a new set of islands, Maldives, was formed. The subsequent eruption of the hotspot 49 million years ago, 45 million years ago, resulted in the Chagos archipelago in Saya de Malha. Although there was a minor eruption 31-33 million years ago, resulting in Nazareth, Cargados Carajos, the hotspot appears to have been relatively quiet between 45-10 million years ago. When it resumed 10 million years ago, it resulted in the formation of Mauritius and Rodrigues Ridge. The Mauritius Islands formed 8 million years ago, and the Reunion Islands appeared 2 million years ago. The volcanic hotspot is currently under the Piton de la Fournaise southeastern corner of Reunion, which briefly erupted in February 2019. Searching for signs including the Iceland hotspot, under the island of Iceland in the North Atlantic, a far hotspot, located under northeastern Ethiopia, the 90 East Ridge formed by the Kagelan hotspot, scientists believe there are about 40 to 50 hotspots around the world. A geological process called intraplate magmatism triggers these hotspots and the flood basalt event. The Reunion hotspot was triggered 65 million years ago, resulting in Deccan traps. The Kerguelen hotspot was activated 117 million years ago, creating the Rajmahal traps in the Bengal-Bihar region of the Indian subcontinent. The end Triassic event resulted in the extinction of marine and terrestrial life. It was accompanied by substantial volcanic activity, sea level rise and depletion of oxygen in the oceans. Likewise, during the late Eocene 30.5 million years, perhaps triggered by several bulky meteorite impacts, the Earth's abrupt cooling was marked by large-scale marine life extinction. From hotspot-induced flood basalt events to massive extinction of life have occurred many times. The team, which included Ken Caldeira Department of Global Ecology, Carnegie Institution for Science, and Yuongju Center for Data Science, New York University led by Rampinoer, first collected data on the geological events in the past 260 million years. The team identified 89 major events. This included 29 global sequence boundaries reflecting sea level fluctuations, 12 marine extinction episodes, 9 non-marine tetrapod extinction events, 13 continental flood basalt eruptions, 10 major ocean anoxic events, 8 times of changes seafloor spreading rates and 8 global pulsations of intraplate magmatism. For each of these events, the team also estimated the age of occurrence using the latest dating techniques. Teasing out a pattern from these seemingly unconnected events was not easy. Like the mythical bird, Hamsa, the swan, in the love story of Nala and Damayanti, could separate milk from water from a mixture of the two, the mathematical technique called Fourier analysis, invented by Jean-Baptiste Joseph Fourier, a French mathematician and physicist, was used by the researchers. Fourier analysis enables one to extract periodic functions that make complex signals, akin to tasting food and finding the ingredients that go into making it. When two waves are added, they produce a complex wave. Likewise, when we have mixed waves, we can decompose them into simple periodic waves. Using this powerful mathematical tool, the researchers found out that geological events have a 27.5 million year major cycle and a possible 9 million year to 10 million shorter period cycle. While this study looked at several diverse geological events over 260 million years, another study looked at only the data from sea level changes. Collating data going back around 600 million years, the study found a cycle with 27.5 million years, lending credence. Cosmic vibes. If the axis of the Earth was not tilted, we would hardly have any seasons on Earth. We know that the season's rhythm is to do with the tilt of Earth's axis and periodic change in the solar flux at a particular location. The sun's rays are straight during the summer, and the sun climbs over our head in the sky. On the other hand, the beams are slanted, and the sun is always low on the sky during the winter. This change in the energy flux drives the onset of the seasons. What drives geological events periodicity of 27.5 million years? One speculation points the finger at the internal Earth processes. The lid covering the vessel with hot water kept over an oven will periodically lift. As the steam builds up, the gas pressure goes up, the cover lifts. The steam escapes, and again the pressure inside the vessel drops. Once again, only after sufficient pressure builds up, the lid will lift up. In like manner, the pulsation tectonics involving the cyclic eruption of plumes of hot mantle material could drive cyclical geological events. The study showed that 7 out of the 12 marine extinction events and 6 out of the 9 non-marine tetrapod extinction episodes in the last 260 million years had also occurred when a continental flood basalt volcanism triggered the formation of new volcanic hotspots. Of these, 3 cataclysmic geologic events also happened when large meteorites with more than 100 kilometers in diameter collided with Earth. Such co-occurrences suggest some causal connection or synergistic effects between significant impacts and flood basalt volcanism. Maybe the impact triggered the volcanoes, which in turn increased volcanic CO2 release, abrupt and severe climate warming, oxygen depletion of oceans and consequently marine extinction episodes. Another theory looks up to the changes in the Earth's orbital cycles. The 3 Milankovitch cycles of changes in the eccentricity, obliquity, and precession of Earth could have a role in driving geological dynamism. Eccentricity measures how much the shape of Earth's orbit departs from a perfect circle. In a cycle that spans about 100,000 years, Earth's orbit changes from near circular to more elliptical. The angle of Earth's axis of rotation, called obliquity, oscillates between 22.1 and 24.5 degrees perpendicular to Earth's orbital plane with a periodicity of 41,000 years. Earth's axis is currently tilted 23.4 degrees. As Earth rotates, it wobbles slightly upon its axis, like a somewhat off-center spinning toy top called axial precession. This has a periodicity of 25,771.5 years. Milankovitch cycles can increase or decrease the ratio of water and ice on its surface. These loading and unloading of water and ice could modulate the tectonic processes and trigger periodic geological events. Another bold possibility the researcher advances has to do with the elusive and enigmatic dark matter. Observations tell us that the outer parts of galaxies rotate faster than they should. Astronomers speculate a mysterious matter, dubbed dark matter, gravitationally propels the stars in the outer regions of the galaxies to move faster. Dark matter is not evenly distributed around the galaxy, it is denser along the galactic plane. The orbit of the Sun and the Solar System around the center of the Milky Way is not planar but oscillates vertically with a period of about 29–35 million years. When the Solar System is aligned with the galactic plane, the interaction of the disk dark matter is higher. Perhaps during this phase, the dark matter perpetrates the Oort cloud, home of billions of space rocks, hurling some of them towards their collision course with Earth. Dark matter could also cause thermal and geophysical disturbances in the inner Earth. All these, researchers say, could lead to significant disruption resulting in overwhelming geological events. Please save the trees and nature, please subscribe to our channel. Thank you.